All right, guys, 2019 free response question number 4 deals with a cylindrical tank right here. Interesting thing right off the bat about a problem like this, it's being filled with rainwater, so our height of the water is rising, which made me think it was going to be a related rate problem right away, which in a way it is. But the odd thing about it is that with a cylindrical tank, your cross-sectional areas are always going to be the same. That's going to be different than a lot of those problems that we saw that dealt with a conical tank, where the water level rose very, very quickly at the beginning and then really slowed down a little bit after that. So that might make this problem a little bit easier, but let's take a look at what's been going on here. We were given the derivative of height with respect to time. And as an insult here, you guys should be offended by this, they felt the need to give you the formula for the volume of a cylinder like you didn't pass 7th grade pre-algebra. Whatever. Anyway, let's take a look at what's going on in part A right here. We're supposed to find the rate of change of the volume of the water in the barrel with respect to time. Yep, right away. Those are the words we were looking for to tell us that this is in fact a related rate problem here. Now this might be superfluous. We'll see when the height of the water is 4 feet. That information would be really important in something like a cone, but in a cylinder where everything's the same regardless of how high the water level is, I'm not sure that's going to end up mattering. And this is something you always want to be on the lookout for, and you might want to circle as soon as you see it to indicate units of measure, because that's something that people can forget to do with some regularity. So let's take a look at what's going on in part A up above right here, guys. So, like most related rate problems, I always like to write out the derivative that we know. dH dt was a negative 1/10 times the square root of h feet per second. And the derivative we want then, it says find the rate of change of the volume of water in the barrel with respect to time. So we want the derivative of volume with respect to time at the moment in time when h is equal to 4. Now remember, that right there, everybody, is what we called back in the end of chapter 4 here a time-specific value. The height of the water in the tank isn't always 4 feet. That only happens at one instant, and we want to be careful not to use that value until after we have differentiated. So if we know this derivative and we want this derivative, we need an equation that relates height with volume. And as every good middle schooler could tell you, volume of a cylinder is going to be pi r squared times h. Now, the interesting thing about this is, though, because of the fact that we're dealing with a cylindrical tank, this diameter right here of 2 feet remains fixed. That is not a time-specific value. This is constant. So the diameter is always going to be 2, which of course means that your radius is always going to be 1, regardless of what time we are at. So in this volume formula right over here, I went ahead and replaced the r with a 1, again, because that is a constant value that's never going to change. And we ended up with this really boring formula that the volume of this cylinder was simply pi times h. But now that we know that v equals pi h is the equation that relates volume with height. So I drew my dashed line right there just to keep myself organized, and I went ahead and differentiated both sides with respect to t. So the derivative of volume with respect to time was equal to, and this derivative was simply going to be a pi times a dH dt. Now, with these two variable quantities, one of them was already known. dH dt was the negative 1/10 root h. So we put that in right here and got a pi times that value and got negative pi over 10. And at this point also, we went ahead and put in the value for h here, which was time specific, at h was equal to 4. So that square root of h now became a square root of 4, which was a 2, and we got a negative pi over 5. And they did ask again for units, so volume over time is going to be in cubic feet per second. And that's the end of part A. All right, let's move it on up right here to part B, where they asked us when the height of the water is 3 feet, is the rate of change of the height of the water with respect to time increasing or decreasing? And we were supposed to explain our reasoning there. Okay, as soon as you see a question of increasing or decreasing, one of the fundamental concepts all year we've learned is that the sign of a function's derivative tells you its behavior. So what we needed is an expression right there that told us the derivative of the height of the water. So here we go for part B. We knew, everybody, right here, the derivative of that was already given to us, that the derivative of height with respect to time was a negative 1/10 times the square root of h. Knowing what I was going to need to do with that in a minute, I went ahead and rewrote that just a little bit. So that's where we had right here, but what we needed to do was find the derivative of the rate of change of the height function. We basically needed the derivative of this derivative. So the derivative of dh dt, Leibniz's notation, we call that a d2h over a dt2, was this. The 1/2 gets multiplied by the negative 1/10 to make a negative 1/20. That's now an h to the negative 1/2, so that's a square root on the bottom, and then, oops, let's ignore that, times the chain rule now, the derivative within dh dt. Well, that dh dt right there is the original derivative we were given up above. So we had to multiply the negative 1 over 20 root h times a negative 1/10 square root of h. And what we can see here nicely is that those square root of h's cancel each other out. The negative times negative is a positive, and we end up with a 1/200th for the value of the second derivative at this particular time. Now, what you'll notice I haven't used, and I don't think I'm going to need to use, is the idea that we were talking here in part B about when the height of the water was 3 feet. Again, I don't think that ended up being relevant in this problem here at all. So, since the derivative of the derivative of height with respect to time was going to be positive, we knew that the rate of change of that water height function right there was going to be increasing. Okay. All right, so that was part B. And then let's take a look at C and see what's going on there. At a time of t equals 0, the height of the water is 5 feet. That is what we call an initial condition. And when they said this, they kind of gave us a hint here. Use separation of variables to find an expression for h in terms of t. I never really looked at this as this type of problem before, but given the fact that they gave you a derivative right here, and they're asking us now to solve for h in terms of t, this is really a differential equation that they're asking us to solve, and the phrase separation of variables was indicative of that as well. So let's take a look at what's going on here in part C. So we had this derivative right here, the same one we've been using in all three parts here, and here's our initial condition that at a time value of 0, height was equal to 5. So to separate those variables, we've got to bring the h over to the left and this dt over to the right. That's an h to the 1/2. When we divide by it, it becomes an h to the negative 1/2 over here on the left times dh. And on the right, there's just the constant, and then we'll multiply that dt over. So that is a relatively quick way to separate our variables. And now we're ready to go ahead and do an integral of the left and an integral of the right. So anti-differentiating right now, we are going to get a 2h to the 1/2 on the left. On the right, we're anti-differentiating a constant, so we just stick that t in front of it and a plus c. But now is the time to use that initial condition right here now and figure out what c is actually equal to. So, kind of indenting here, the h value was 5, so I did 2 times 5 to the 1/2, which I wrote as 2 root 5, is equal to a negative 1/10, t was 0, and a plus c. Well, that whole term just wipes out, and we end up with c is equal to 2 root 5. So back to where we were on this line here, 2, and I rewrote that as a square root of h, is equal to a negative 1/10 t plus that c value of 2 root 5. And now from here, 2 steps to solve for h. I divided everything by 2 and got the square root of h to be a negative 1/20th t, plus the 2's canceled here, and we just got a square root of 5. And the last thing we had to do to solve for h was to square both sides. And I really hope nobody's going to make the silly mistake right here that I could see people making of thinking that if you wanted to square a binomial, you just square each term. So I wonder if I wouldn't see some of this. 1 over 400 t squared plus 5. That's what you would have gotten if you had just squared this term and squared this term separately. But that is not correct, because as every Algebra 2 student can tell you, when we square a binomial, you got to use parentheses, and either you get a trinomial when you multiply it all out, or at this level, we're not that interested in Algebra 2, so we're just going to leave it as a binomial in parentheses squared, and we're going to quit there.